Welcome to Easy BTech, your guide for BTech and beyond. My name is G. Sampath. I'm going to discuss the subject VLSI design. Today, we are going to discuss the topic Mass Transistor, Mass Transistor, Transconductance. Transconductance, it is representation GM, and then we'll discuss the mass transistors. Now, what is the transconductance of a mass transistor? Transconductance is defined. Transconductance GM is defined change in output current, change in output current, output current. So that is we call IDS, change in IDS, change in output current from drain to source with respect to with respect to with respect to change in input voltage, change in input voltage, that is VGS, change in input voltage. So that is change in VGS. You see the definition here and a formula representation. GM is equal to change in IDS by change in VGS, where VDS is constant, keeping VDS is constant. So this is a definition and a formula representation of transconductance. So it is a drain to source current. IDS is the change in drain to source current with respect to this change in gate to source voltage, VGS, change in input voltage, so that the current flow through IDS will be changed. Let us see in the symbol. So this is the VGS we are applying to the MOS transistor. Let us take it is a NMOS transistor. VGS we are applying external gate voltage, gate to source voltage, and this is VDD, and this is VSS, and there is a current flow through this one is called IDS. We are taking voltage from here to here is called a VDS, drain to source voltage. So the current through this drain to source is depend on this external gate to source voltage. So is called as a transconductance. So if you are increasing the transconductance in the device, the switching speed, so speedily it will be on or off. Increasing transconductance, increasing GM in mass transistor in the device, mass transistor. So increasing GM in the device, in the mass transistor, we can say mass transistor. So it is speedily switch on or off. So it is speedily on or off. On or off will be happened very fast, very fastly. That is the purpose of this transconductance. So change in output current with respect to this VGS. So let us derive this. What are the parameters involved in this transconductance? So first one, we have a formula. According to the formula, change in IDS is there. Change in IDS is there. So change in IDS, we already derived the drain to source current equation in NMOS transistor. Charge induced in the channel by transit time between source and drain. So this is equal to QC is the current through drain to source because of charge induced in the channel by applying gate to source voltage. Charge induced, charge induced in the channel, charge induced in the channel divided by transit time between source and drain. We call it is a transit time between source to drain. Right, we already derived this transit time, and let us see the QC substitution. Then we substitute this IDS. Then we can find out the what are the parameters involved in transconductance. So change in IDS is equal to QC by transit time means L square by mu VDS. This is we derived in NMOS transistor current equation, drain to source versus IDS and VDS relation, L square by mu VDS, L square by mu VDS. So simplifying this, QC into mu VDS by L square. L is the length of the channel, mu is the mobility of charge carriers, VDS is the drain to source voltage. So mu is the mobility of charge carriers, mobility of charge carriers, mobility of charge carriers, mobility of charge carriers. VDS is the drain to source voltage, drain to source voltage, drain to source voltage, and L is the length of the channel. L is the length of the channel, length of the channel, length of the channel. Now, what is QC? QC is nothing but capacitance CG into change in VGS, where this is this equation from the capacitance is equal to charge per unit voltage, charge per unit voltage, where then Q is equal to C capacitance C into V. So charge induced in the channel is equal to gate to channel capacitance into change in VGS. So change in VGS. VGS is the input voltage, gate to channel capacitance. Now we can substitute this in change in IDS is equal to the previous expression. This one is QC by L square into mu VDS, mu VDS. So substitute this QC, substitute the QC, substitute QC in IDS equation, in IDS equation, IDS equation. You see what happens, change in IDS is equal to charge induced in the channel. So it is Cg into change in VGS and the remaining term mu into VDS by L square. So we got this IDS. Now substitute this in change in IDS in transconductance. So we have transconductance. Transconductance is equal to, then substitute this one. We have write the formula, then you can substitute. So change in IDS by change in VGS. This is equal to Cg into change in VGS into mu VDS divided by change in VGS into this L square into L square. Now this change in VGS will be cancelled out. Now the equation, we can simplify this. Transconductance is equal to Cg into mu VDS by L square. Okay. Now if saturation region VDS is equal to VGS minus VT. This is in saturation region. Saturation region. Now Gm is equal to Cg into mu VGS minus VT. Substitute the Cg value. What is the gate to channel capacitance? Cg is equal to epsilon insulation, epsilon naught W into L by D. So this is a gate to channel capacitance. Let us take this one. Cg is equal to epsilon insulation, epsilon naught W into L by D. So gate to channel capacitance means it is a polysilicon and below SiO2 layer and in channel area. This is a channel area. Polysilicon, this one is a polysilicon. Positive charge carriers. SiO2 layer is a dielectric layer. And if you take Nmos transistor, it is a N diffusion over here. N diffusion, source, drain, and this one is a gate terminal. So gate to channel capacitance. Polysilicon is a gate to channel capacitance. So negative charge carriers and positive charge carriers. And the channel area is negative charge carriers are formed. You see, so capacitance is nothing but two positive plate, positive one negative plate with a dielectric layer. Two plates, positive or negative plate, positive negative plate with a dielectric layer. So C is equal to epsilon A by D. C is equal to epsilon A by D. So epsilon is a dielectric layer. D is the distance between dielectric layer. Okay, and A is the area of this plate. So width and length. Here, width of the polysilicon and this length of the channel. This is the length of the channel area. So this is called a CG, gate to channel capacitance. So positive plate is a polysilicon, negative plate is a channel area, and in between SiO2 layer is there. This is a dielectric layer. SiO2 layer is there. So that is called epsilon insulation. Insulation layer is a SiO2 layer. Epsilon naught is some free space is there. By applying external charge carriers, W is the width of the polysilicon, L is the length of the channel, D is the thickness of this one. So that is called as a gate to channel capacitance. Cg we can write here. Cg is a gate to channel capacitance. Charge induced by applying external gate voltage. Gate to channel capacitance. Gate to channel capacitance. Now substitute this one. Substitute over here. So we have the equation transconductance is equal to Cg into mu VGS minus VT. It is a saturation region. VDS equal to VGS minus VT, and here divided by L square is there, divided by this L square. Now divided by L square, you can substitute this one Cg value. So what is the Cg? Epsilon insulation, epsilon naught W into L mu by D into this L square is there, into this VGS minus VT. Now L and square will be cancelled out. Then the final transconductance of a MOS transistor, GM, transconductance of a MOS transistor will be equal to epsilon insulation, epsilon naught W by L into mu divided by D into this VGS minus VT. So this is the final equation of a MOS transistor transconductance. If the transconductance is increasing, the switching speed of the MOS transistor will be increased. Means it will be speedily on and speedily off. So that is a working of the transconductance. Next we will see the PAS transistors. The PAS transistors. Let us see the PAS transistor. What is a PAS transistor and why it is used in MOS transistor? PAS transistor. PAS transistor is nothing but it carries the switch logic when transistors are in series connected. So it is defined. Transistors are connected in series. Transistors are MOS transistors. Transistors are connected in series. Transistors are connected in series. Logic signal pass through is called as a PAS transistor. So let us see this one. A series connected NMOS transistors. It is like a switch. You see, it is like a switch on and off by applying a gate voltage. Relay switch. It is like a relay switch where we can on and off by applying a open and closing the switch. Then the signal, electric signal passing through this. Here logic is passing through this. So VDD here, let us say it is a ground signal. So input is applying A, B and C. Here 3 transistors are there. These 3 transistors are connected in series. So passing through this logic VDD through this. When the gate voltage you are applying, so like a relay switch. A relay switch is a switch when where we can open and close the signal pass through this. So it is a gate voltage here opening and closing, the signal passing through this. If the transistors are connected in series, it is called as a pass transistor. It passes the signal through these transistors. Transistors are connected in series, it passes the signal through when the gate voltage is applied. So it is a NMOS transistor connected in series. So X is the output voltage signal. When we take here, A is equal to 1, B is equal to 1, C is equal to 1. It is seriously connected. So NMOS is on, NMOS on, NMOS on, NMOS on for logic 1, for logic 1. So logic 1 it will be on. Logic 1 it will be on. C is also logic 1 it will be on. Then the signal will be passing. So 1 this will on. This is on. B it will be on. B is equal to 1 it will be on. C it will be on. Then the signal passing through this. So it is act like a AND logic. A into B into C. It is a AND logic. So series are seriously connected transistors. The logic applied is AND logic. AND logic. It is a AND logic pass transistors. AND logic pass transistors. Signal through this, when you are applying gate voltage, A is equal to B is equal to C is equal to 1. If anyone, it is like a AND gate. AND gate means when it will be on, both inputs are, means inputs are high, then only it will be high, otherwise it will be 0. So AND logic, AND gate, if you see AND gate, so it is AND logic, it acts as a AND gate, AND logic, both inputs are 1, then only output 1, otherwise any one input will be 0, it will be 0. So it acts as a AND switch. So if A is equal to 0, then no signal, it will be open, so no signal passing through. If B is equal to 0, it will be open circuit, so the VDD signal cannot pass till end of this X. If C is equal to 0, so it will be disconnected, so VDD cannot pass through this, so it will not so it act as a AND gate. So all inputs are 1, then the switch will be closed, then the signal will be passed. So AND logic is applicable this pass transistor when these are connected in series. Let us see, the pass transistors are MOS transistors, series and parallel transistors, series and parallel transistors. What is the logic? Let us see. And when we are using this series and parallel in designing of CMOS, NAND and NOR, series and parallel transistors. Okay. Now series transistor, NMOS series transistor. If NMOS are series, let us see this one. So this is one of the important information about pass transistors when you are designing of CMOS NAND gate, CMOS NOR gate, NAND NOR gates designing, the pass transistors, series and parallel transistors are used in CMOS design, complementary MOS transistor design. So this is input A and input B. Input A, input B. You see this one, it is VDD and VSS. Okay. So whenever A is equal to B is equal to 1, it acts as a AND logic. AND logic means so output is A into B. Output is A into B. The signal flow through this, it is A into B. A into B. So let us see the truth table of this one. Truth table of this one. 0 0 0 1 1 0 1 1. So logic through this seriously connected, the logic is AND logic. 0 0 is 0, 0 1 is 0, 1 0 is 0, 1 1 is 1. So whenever both inputs are 1, then output is 1. Then output is 1. So otherwise it should be 0. Otherwise it should be 0. It will be 0 or it will be 1. Then it will be 0. So it is a AND logic implementation. So series connected. NMOS are series connected. So this is a NMOS series. This is NMOS series connection. Series connection. NMOS series circuit. NMOS series circuit. Let us see this one. If NMOS are parallel circuit, then what happens? If NMOS NMOS are parallel, then what is the logic? Then what is the logic? NMOS are parallel, then what is the logic? Input A and two input NMOS transistor, VDD and VSS. So NMOS transistors are parallel. The logic of the circuit is A plus B. It is OR logic. OR logic. OR logic. Series it is AND logic. We call it is AND logic. AND logic. Now you know OR gate truth table 0 0 0 1 1 0 1 1. Then output is A plus B 0 1 1 and 1. Any one will be 1. Then output is 1. If A is equal to 1, this will be on. B is equal to 0, this will be disconnected. Then output is taken, it is 1. So A is equal to 0, B is equal to 0. Both are 0, both are off. Then the output here will be taken VDD to VSS. The output is VDD to VSS is taken 0. If A is equal to 0, B is equal to 1, then the VDD to VSS is 1. 1 0. Then VDD to VSS is 1. If 1 1, VDD to VSS, it will be 1. So it acts as a OR logic circuit. Let us see the Pmos transistors. Similarly, Pmos transistor, Pmos series. Now what happens? NMOS and Pmos are used in Cmos design. Pmos series. So Pmos is a complementary MOS of NMOS. So it is a complement of NMOS. So Pmos are series. What happens? You see this one. So Pmos. If two Pmos transistors are series, now what is the logic? What is the logic from VDD to VSS? What is the logic from VDD to VSS? So Pmos is on. The input is A complement. Input is A complement here. And another input, when Pmos is on, the input is B complement. It is on for the logic 0. It is on for the logic 0. So NMOS transistor, we are seeing this. A is equal to 1, B is equal to 1, C is equal to 1. Then it will be on. There is a path between drain and source. In Pmos transistor is a complement logic. A is equal to 1, NMOS on. A is equal to 1, A is equal to 0, Pmos will be on. So logic is, the output logic from VDD to VSS is A complement into B complement. A complement into B complement. It is a complement of NMOS transistor. Let us see this one. AB truth table. So for example, we are applying logic 0 0 0 1 1 0 1 1 we are applying. So A complement 0 complement will be 1 1 here 1 here 0 here 0, and B complement, take B complement. B complement 0 is 1 0 1 and 0. So output is A complement into B complement. Output is A complement into B complement. So and of this A complement and B complement, so 1 into 1 1, and this is 0 and this is 0 and this is 0. So it is a complement of NMOS series. NMOS series, you see. So NMOS or series, it is AND logic. So AND gate logic. So what is the output here? For 0 0 0 1 1 0 1 1 0 0 0 1. Now if Pmos are series, so what is the logic here? Complement of AB. Complement of AB. You see this one, complement of AB. A complement into B complement. So complement of AB, it is 1 0 0 0. Now Pmos are parallel. Now Pmos parallel. It is complement of NMOS parallel. So when Pmos are series, it is complement of NMOS. Pmos are parallel, it is complement of NMOS parallel. Now let us see the diagram here. Pmos are parallel. Pmos are parallel. You can see this one. Pmos are parallel. This is A complement. Input is A complement. Then it will be on. B complement. It will be on. Now we take the signal from VDD to VSS. VDD to VSS. The logic is parallel. Means A plus B, but it is A complement plus B complement. A complement plus B complement. Now take the truth table AB. So two inputs are there, logic 0 0 0 1 1 0 and 1 1. So logic we can take A complement, B complement already taken above that one. Directly I can take the result A complement plus B complement. A complement plus B complement. So it is a OR logic of this A complement plus B complement. So 1 plus 1 it will be 1, 1 plus 0 it will be 1, 0 plus 1 it will be 1, 0 plus 0 it will be 0. So it is a complement of A plus B. It is a complement of A plus B. You see this one. It is a complement of A plus B. So Pmos is a series. It is a complement of AB. Pmos is parallel. It is a complement of NMOS. NMOS parallel. Now, if you design a CMOS, if we design AB complement, if you design NAND gate, AB complement means NAND gate. If you design NAND gate, now by using CMOS, by using CMOS design, if you see this one, so how it will be designed? AB series, NMOS or series. AB means is a AND logic. AND logic means A and B are series. You see this one. A and B are series. A and B are series. And this complement is there. So we have De Morgan's law, AB complement. AB complement is equal to A complement plus B complement. A complement plus B complement. A complement plus B complement in Pmos. So where it is A complement plus B complement. You see this one. So complement logic is parallel. Complement logic is parallel. So Pmos are parallel. Pmos are parallel. You see this one. So this is a designing of NAND gate by using two transistors, NMOS and PMOS. NMOS and PMOS transistors. So this is A and B. So A and B are series. Then complemented logic. Output is A B complement. It is a NAND gate. So it is pull up transistors and pull down transistor. PMOS transistor and NMOS transistor, pull down transistor. So ABR series, PMOS are parallel logic. It is AND gate design. The complement is the complemented transistors. So by using this De Morgan's law, AB complement NAND gate designing, the complemented transistors are A complement plus B complement. These are parallel. Okay, so this is a representation of past transistors, series and parallel NMOS and PMOS, and we discussed the transconductance of MOS transistor. Okay, please subscribe the channel, like and share with your friends. Thank you.